Okay, hello and welcome to class 7 of Physics 350. This class is on the electric potential, and this covers section 2.3 of the textbook. And the electric potential is a very useful quantity in electrodynamics, and it's also known as the voltage, same as the voltage like 40 watt or 100 watt bulb or 110 volts coming out of an outlet. But we define it a little bit more technically in electrodynamics and mathematically using the concepts that we've developed so far from the line integral and so forth. So the electric potential is defined as the line integral from a given origin that we pick somewhere in space, O, along a path of the electric field to a final position R. And the electric potential is a function of this final position R. Okay? So one thing which we've learned in problems so far is that, or that one general property of line integrals is that line integrals don't always have to be the same if we take different paths to go from one end to the other. So, but it turns out that the fact that, as we learned in previous classes, the curl of E is equal to 0, okay, the curl of E is equal to 0 for electrostatic fields, guarantees that this line integral definition of the electric potential doesn't depend on the path. Okay, it doesn't depend on the path that's being taken. So whether we go along the path shown here, or we take another path here, or we take a third path here, we actually get the same value. And I'm not going to prove that here, go into too much details, but back in the section on the curl and line integrals, section 1.6, theorem 1 shows that the curl of a vector field being 0 means that the line integral doesn't depend on the path. Okay, so rather than the absolute electric potential, which we might call this, what's often more important in physical problems is the difference in electric potential between 2 points. We call V of say point B minus V of point A. So we can apply this definition here, and we have, so if we put in for, if we plug in for R, B, and we plug in for RA over here, we have V at point B is just minus the line integral from O to B of E dot dl, just like the definition. And then since there's a minus sign here, we have plus the integral from 0 to A of E dot dl. And then we can make one more adjustment, keep the first term the same. The second term, if we flip the limits of integration, O and A, we just get the minus the integral from A to O. But then if we look at this, we have the integral from A to O and the integral from O to B. That becomes the integral from A to B with a minus sign. So we get that the voltage, or excuse me, the electric potential at B minus the electric potential at A is equal to minus the line integral from A to B of E dot dl. Okay? And that's independent of path by the properties of the fact that the electric field has 0 curl. Okay, so but what does Green's theorem tell us about the difference in the value of V at position B and position A? V of B minus V of A is equal to the integral, according to Green's theorem, from A to B between the endpoints of the gradient of V dot dl, right? If you look back to Green's theorem, that's what it would say about any function. It was t back then, but it equally applied to V here. And so if we look at these two expressions, we have V of B minus V of A is equal to minus the integral of E dot dl. Here we have it's minus the integral of gradient of V dot dl. So this is true for any path and for any electric field. And so it must be true that the integrands are equal. That is, that the gradient of V is equal to minus E, or we can say E is equal to minus the gradient of V. Okay? And this is a lot of the reason why we define the electric potential, because it's a scalar, okay? It's a scalar, and in many cases it's easier to calculate than the electric field, which is a vector field. And once we get the scalar electric potential, we take the gradient, we get minus the gradient, we get the electric field immediately, okay? But you might be asking a question, or at least this question might make sense to you. How is the electric field, which contains three pieces of information, x, y, z components, at every point in space, how is that equal to, or how can that be represented by a scalar function which only has one piece of information at every point in space? And again, it's the fact that the curl of E equal to 0 explains that. The curl of E equal to 0 puts certain restrictions on the components of E. E is not an arbitrary vector field, but it's a, there are certain restrictions having to do with mixed partial derivatives, which come when you apply the definition of the curl to E. And that explains why the information in the vector field E can be contained in a scalar function V, which appears to have less information. Okay, so what about this reference point? This reference point O, which we seem to pick out of thin air. Well, suppose we pick a difference reference point. Okay, so on that same picture, suppose I picked O prime, okay, which is a little bit displaced from O. And then instead I defined V prime of R over here as the integral from O prime to R along this path of the electric field, okay? Is that going to give me different results? Well, yes and no. It's going to give me a different value for V prime will be different than V was before, but it's going to turn out it has no effect on the electric field, which is what we really physically care about, because the electric field causes forces. So we can write this as the integral from O prime to O minus the integral from O to R. So we go from O prime to O and O to R, and that is the same as going from O to R, O prime to R, okay? But the integral from O prime to O is just since it's independent of path, is just some constant, which we can call K. And this second integral here is what we call V of R before, as opposed to V prime, okay? So shifting the origin just has the effect of changing the electric potential at every given point in space by some constant K, which is equal to the line integral between the two reference points. And if we look at the electric field, which comes from this new V prime, we have minus, remember we've learned that the electric field is minus the gradient of V prime. So plugging in here, that's minus the gradient of this constant plus V of R. But the gradient of a constant, since the gradient is a derivative, is going to be 0. So we have minus the gradient of the constant 0, V of R, so we just get minus the gradient of V back again. So the electric field which we get from this definition with a different reference point is not affected. It's still equal to what we got before. And so we have a freedom to choose our reference point when we define the electric potential, because it doesn't have any effect on the electric field which we get because of what we've just talked about here. And we usually take V of R is equal to 0 when R is at infinity. Okay, we usually, not always, but oftentimes it's most convenient to let the electric potential be 0 at infinity, as in the case of a point charge. Okay, so let's look at the potential of a point charge. You probably remember that the electric field of a point charge is a constant. You may remember it as K, but written out in fancy terms, it's 1 over 4 pi epsilon naught Q over R squared R hat. So here's a picture of it in 2 dimensions. For a positive point charge Q, it just goes out in all directions, and it falls off in strength as 1 over R squared. So to do the line integral, which we're going to need to get the potential, we're going to use spherical coordinates, which makes sense since this is spherically symmetric. So our dl is going to be what we learned in spherical coordinates. It's going to be dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. And so we can go ahead and do our integral using our definition. The electric potential is the integral from some origin, which we're going to pick our origin. It'll turn out to be at infinitely far from the point charge. That's where we're going to pick it to be 0. But anyway, from the origin to R of E dot dl. And then if we look at E, it only has an R hat component. So E dot dl only picks up this dr. We have a negative sign. So grouping terms, we have Q over 4 pi epsilon naught dr over R squared. And just for convenience, I've made this a dummy integration variable, dr prime over R prime squared, so we can have R as our limit of integration. Okay? And then the antiderivative of 1 over R prime squared is minus 1 over R prime, evaluated from infinity to R. And so that gives, well, we have minus minus, so that just gives 1 over R, and then when we put infinity in here, we get 0. 1 over infinity is 0. So we just get 1 over 4 pi epsilon naught Q over R, or KQ over R, which you may remember for the potential of a point charge from Physics 202. And it just looks like this. For a positive point charge, if Q is positive, it diverges to positive infinity when R is small, and then it diverges, or excuse me, it decreases to 0 as R goes to infinity, as we chose it would by choosing our origin at infinity. And for a negative point charge, a negative Q, it's just going to go to negative infinity as R goes to 0. Okay, so a sample integration for the potential, just to show, although this one's a wee bit complicated, it's a little bit easier. It's going to be parallel to the example we did in the last class for the electric field. And but it's going to be a little bit easier to do, a little bit less involved, and so hopefully show the value of the electric potential. Okay, so how do we handle the integral of the electric potential? B at a given point R, we add up over all of the region of charge, which is contributing, all the little pieces dV of electric potential that are coming from that. And since we know that V is Q over 4 pi epsilon naught R from the last slide, that's going to be dQ, and I've put a prime here to indicate the prime dQ prime indicates that these are source charges. Those are the charges that are causing our electric field. And here's this diagram, which you might recognize from the last video. It's got a linear charge density from minus L to L here of linear charge density lambda. And we're trying to find now the electric potential at point P as opposed to the electric field at point P, okay? So remember that script R is a vector which points from the source, okay, the source, for example, this little bit of charge dx prime or dq prime corresponding to the length dx prime to the desired point P. Okay, so can go ahead and set up the integral. We don't have to worry about vector components in this integral because the electric potential is a scalar. So we get V is equal to 1 over 4 pi epsilon naught times the integral from minus L to L, since that's the range of our charge, times dq prime, which will be the linear charge density, times dx prime, the charge per unit length, times the length, over the length of this separation vector, which is the square root of z squared plus x prime squared. Excuse me, this should read x prime here, not x. Okay, so that's just an integral, which we can evaluate. It turns out it's kind of tricky to evaluate, but it's we can do it using Mathematica, and it turns out to be this: lambda over 4. We pull the lambda out. The integral of this is just the natural log of 2 times the square root of z squared plus x prime squared plus 2x, evaluated from minus L to L. Okay, so I know that's not a nice, neat and tidy integral, but notice that it's only taken us 2 steps as opposed to 5 or 6 steps when we were calculating the electric field to get the electric potential. And when we evaluate from L to minus L, we just plug in L for x, or x prime rather, and we get 2 square root of z squared plus L squared, etc. Okay, so we get this expression here. Okay, not a beautiful expression, but one thing we can check is whether our initial assumption was that the electric field should go to, sorry, the electric potential should be 0 at infinity. Okay, so does the limit go to, as z goes to infinity, do we get v equals 0? Well, as z goes to infinity, this L squared and this L squared and this plus 2L and this minus 2L are going to get smaller and smaller, and we're going to have the natural log of something very large over something quite large plus 2L, where L is small, over something quite large minus 2L. So this ratio will be just a little bit above 1, and the natural log of 1 is 0. So in fact, the limit as z goes to infinity is 0, as we hoped. Okay? And then if we want to find the electric field, which is usually what we're more interested, or just as interested in, we can take minus the gradient, We get, again, using Mathematica, I wouldn't necessarily want to, I mean, this is possible to take this gradient, but it's kind of nasty. We get this expression here, 1 over 4 pi epsilon naught, 2 lambda L over square root of z, over square root of z times the square root of z squared plus L squared, okay? And if you look back at the last lecture, that is in fact what we found for the electric field, the vertical component at this point P, okay? So this agrees with the result from the last class. Okay, so in this class we learned about the electric potential, how it's defined. We learned that it's independent of path because the curl of E is equal to 0. That allows us to define it. We learned that we're free to choose the reference point and that it doesn't affect the magnitude of, or the value of the electric field that comes out. And we saw the electric field, sorry, the electric potential of a point charge and of a small line of charge here. Great, thanks for your attention.